Sure. Okay. Maybe I'll start by introducing myself since it's the first time I come here. So I'm Nicolas Flagey. I'm a senior staff scientist. I'm usually in Mueller. In fact, usually I'm at home. I'm only on Mondays in Mueller. I'm on the telescope branch, and I joined 2.5 years ago. Basically, I work on the telescope of James Webb, trying to make sure that it's always phased and aligned properly so we can do science with it. And I've been collaborating with my PhD advisor, François Boulanger, in Paris, and a former postdoc advisor, Alberto Noriega Crespo, who is here, part of the MIRI branch, on a project, a Cycle 1 project with James Webb to observe the Pleiades. And we invited Guillaume Vigoureux, who's a master's student at the École Normale in Paris, to work with us. He's been here since March, early March. He's going to leave us in a couple of weeks. His whole internship is going to continue in Paris. The goal for him during his visit was to focus on removing stars and galaxies from the data because those are high-density objects. So you won't just look at the low-density universe. Yeah, right?
So thank you. So hello. So I will present you my work. So as Nicolas mentioned, my work was mainly on removing the stars and the galaxy in the Pleiades. So here you have a map of the Pleiades, a large map of the Pleiades taken by Hubble 20 years ago. So I will just first present you my strategy, so the removal of the stars, and then two parts about the removal of the galaxies, because it will be a bit harder, and then I will present you what I have done on my maps and not the theoretical point of view. So first, here on the right, you have a map taken by Spitzer 20 years ago, which is almost at the same wavelength that my two maps taken by James Webb almost 1 year ago. So those two maps are taken like so, around mirror P in the Pleiades. So the first one, you can see the stripes. So here the stripes which are due to mirror P. And the other one, the Earth map, taken further just to have like less stars surrounding. So why did we take those maps? Those maps have been taken because the whole proposal objective was to study the ambipolar diffusion. So what is the ambipolar diffusion? So in the interstellar medium, you have mainly neutral gas and ionized dust particles. Okay, and so the ionized dust particles are linked with the magnetic field. And because the ionized particle and the H2 molecules are linked due to collision, there is a link between neutral gas and magnetic field, even if neutral gas is neutral. And so, however, there is like 1 million more particles of neutral gas than of ionized dust particle. In our case, it's polycyclic aromatic hydrocarbon, so PAH. And so, in fact, when you go to smaller and smaller scale, you should be able to see a kind of decoupling between the magnetic field and the neutral gas. So this is what is called the ambipolar diffusion, and this is why the whole proposal has been done. So there is several filters to see that, but I will only focus on one filter, which is F335M, because I will only focus on the polycyclic aromatic hydrocarbon to see the link between those PAH and the magnetic field. So we mainly focus on the statistical properties of the PAH. So here you have an example of the magnetic field in the Pleiades. So this is the old map, but here you have an example of the magnetic field. And so my point will be to characterize the anisotropies in a statistical way of the dust in this region comparing to the magnetic field. So first I just make a zoom on those two maps to show you that there is not only dust, unfortunately, on those maps, so there is obviously those three big stripes and many galaxies and other bright points. So I will distinguish two kinds of objects. So when it's like point-like sources, you will see like those. It's like what we call stars. And when it's not like point-like sources, you won't see this pattern from James Webb. You will see like those kind of structures. So maybe you have many like galaxies around there. So my point will be first to remove the stars because it's always the same pattern. So it should be simpler to remove them, and then we will try to remove the galaxy using another approach. So first, I just like make a remap. We have two maps. One of what it's called the mirror map, on which we have stars, galaxies, and dust, and another map, the off map, on which we have only stars and galaxies, no dust. So our plan is to tweak, like to work on this map to be able to just obtain a map with only dust. So the first step will be to remove the stars because it's the easiest. So we will try to create an empirical point spread function, PSF, trying to find the fluxes, the position of the stars, and be able to remove all the stars in the off map. And so obviously we will do the same on the map on which there is dust. And then at this point we will have only two maps on which there is only galaxies, and on one of them there is also the dust. So we will need to remove the galaxies. To do so, we will introduce a new approach because, as you can see, the galaxies can have many different shapes. So we can't give them a pattern. So what we will do a decomposition using wavelet. So here we have an example of a wavelet, so a real part of the wavelet. So this kind of wavelet can be changed using different scale. So this is the J parameters, and we can also use different orientation. So this is the L parameters. And so we will create a bunch of different wavelets, and we will decompose a map into those wavelets. So just to give you an example, this is a map taken by Herschel, and you can see like I'm just decomposing using different scale of wavelets, always vertical wavelets, and you can see that there is just like different structure which are just raised by this decomposition. Okay? And as I've mentioned, I can also do this by changing the orientation of the wavelet. And so you can see that I'm just like picking all the kind of vertical structure, and there are all the horizontal structure, and depending on the angles and on the scales, I can extract different kind of structures. Okay, so when I have that, all those maps, because I will use much more wavelets, much more different wavelets, I will create many maps. And I want to create statistics with those maps. What I will do, I will just like compare those maps using covariances. So I will just introduce a small operator to be able to compare maps of different scale, and then I will just like basically do some covariance between two kind of maps. Okay, and those coefficients will give me the correlation between two maps. So if I just compare two maps, if the coefficient is I, it will mean that those maps are really linked. And so this is how I will try to figure out what is the aspect, what is the structure of the galaxies. So, and all those coefficients, I will call them the WPH statistics, are just like the bunch of all those coefficients. And so, using those coefficients, I will just create many white noise maps. And then I will modify them one by one to try to recreate a map which are the same WPH statistics that my map with only the galaxies. And in fact, it will create new maps, starting from nothing, new maps on which there is only galaxies, several different, and on which the galaxy will be in different places. Okay, and so with all those maps, we'll be able to extract the galaxies on the map. So just first suppose that we have only one synthesis, okay? So here, by phi, I just mean the statistics. Okay, so we will start from a P0 map, which is just like a white noise map. We will add to it one synthesis, and then we will just compare the statistic of this map, this added map, to the map on which there is dust plus galaxies. And what we will try to do is try to modify this P0 map to have this added map as close as possible statistically to this map on which there is dust and galaxies. So we hope that it will deform this map up to have like a map which has the same statistics as the dust in the map. So it won't be the exact same map, it will just be a map which has the same statistic as the map with the dust. So, okay, so this is, in fact, I will do that on several syntheses to avoid to have any effect due to the position of the galaxies in one map, in one synthesis. Okay, so when we will have that, we will have a map which has the same statistics as the dust in our map, but not exactly the same structure. So to be able to have exactly the same structure, we will start not from a random P0, but from the map on which there is stars plus galaxies. And then by itself, the algorithm will remove slowly the galaxies, because if you just add galaxies, there are too much galaxies. So it will by itself remove all the galaxies on this map, on this P0 map, and then at the end, we will have the exact same map, but just with the galaxy removed. So to be more concrete, I will show you an example. So we still have this map on Herschel, and here the point was not to remove the galaxy, it was to remove the CIB, just to be able to study the dust. So here we have like a simulation of the CIB and some synthesis. Okay, three of them, there's much more synthesis, but just three of them. And what we do is just like, we just extract the CIB component on this map. So here we have the CIB component, and here you have just the dust. So you can see that it's really good. But in fact, so this method has been already used for this kind of structure, which are like not dense at all structure, really like flat structure. And my work is really new in the sense that it's for really dense structure. And this is the turning point, try to remove dense structure using this kind of WPH coefficient. So let me present you some my work. So I will first start on the thing which is the most obvious on this map, which is this big arm, which is obviously not the best. So here you just like a zoom on this map, on this big arm. And so, So what the first thing I need to do to be able to remove this arm, I will just like remove the background around this arm. So what I do, I just like extract this map, and I just like make a slice, a resultant slice of this arm, just to have like all the pixels. And I just like remove the pixels which are in the center of the pixel on which there is the star. And so they just give me two kind of like the two parts which are on the left and on the right here. And then I just interpolate to estimate the background which is under the star. So then I can just like remove the background, and since the background is removed, I will try to recreate the pattern, because you can see that here there is a kind of pattern. It's not like just a line, there is like some like a structure. So what I will do to be able to recreate the pattern, I will normalize the arm. So I will just like take vertical slices all along the arm, and I will do this for just like the few pixels. So I mean like the 20 pixels which are there, and so all those pixels will give all those like gray lines. And so I will just take the median of those, which will give us the red one, and I will just like fit it with a polynomial to have the blue lines. So here I have the vertical decrease all along the axis, and it will allow me to just like have normalized iron, or. So here, what I do, there is several steps on this slide. So the first step, when I have all those patterns which are normalized, I can just like stack them. So I just like take one horizontal slice and I take the median of the 50 which are above and the 50 which are below. And I stack them to have like the median structure, because there is like stars, galaxies which are under that. So I don't want to have any kind of like residuals due to the galaxy or the stars in the estimation. And then I can denormalize them and just like remove all the estimation of the arm on the actual arm. So here we have just like the different horizontal slices depending on where I am on the arm, and you can see obviously it's brighter when you are at the top and just like darker when you are at the bottom. And you can also see that the arm is not really vertical; it's like slightly moving from the right to the left when it's like decreasing. And you can also see that even the shape of the pattern from like one big spikes then to two big spikes. So it's not like that simple, such a simple pattern. So here you have the before-after comparison. So you can see that I have just like some hidden galaxies for just like be able to be seen using this method. And you can see that right now the image seems like really nice, and we don't have just like this big stripe around. So it's not yet perfect. You have some residual, but I mean like really tiny residual in comparison with like the big spikes we had before. So since this big arm at the center is removed, we'll focus on removing all those stars which are almost everywhere in the map. So the first thing is, once again, to estimate the background. So to estimate the background, because I will try to recreate an EPSF, so I need the background to be removed to be able to compute the EPSF. So the first step, I'm using multiple scales. I'm using box of size like 100 by 100, then 25 by 25, and then 10 by 10. I'm just like putting threshold value to, as much as possible, avoid any contamination due to the stars of the galaxy. And so I'm just like making a kind of blur map of the original map. So you can see that there's still some residuals due to the big arms and some residuals due to the galaxy, but it's almost good. And so then I can just like remove the background. And so here we have the map with the background removed, so you can see almost any background. And then I will just try to pick all the stars. So what I do, I just like see where are the bright pixels. If the pixels are just close together, I just like consider that to be one object. And then I have to differentiate between galaxies and stars. And then when it's done, I have like a collection of stars which are centered using the center of mass. But in fact, those stars are not like really perfect stars. They're not totally isotropic. So the center of mass is not a good center. So what I have to do is to find a better center. So what I did, I created a theoretical PSF using a Python library which is called WebPSF. So this is a theoretical PSF. And then I use it to recenter in 2 dimensions all the stars. So, but in fact, the main trouble with the theoretical PSF is the core because it's really overestimated. So I just like remove it. And another problem is that because far from the center, obviously the standard to noise ratio is worse and worse. So I'm only focusing on the fit is only done on this region, so on this ring, which is between 45 pixels and 9 pixels. And there I can do the fit to try to make the best estimation of the right center of each star. And then I can just like pick the 25 brightest stars, just like recenter them using the theoretical EPSF, then normalize them and stack them to create the new EPSF. So here you have the EPSF we created. So it's just an extract of like a larger map, but you can see that, as I told you, the core is really different. The arms are also quite different, but maybe it's like harder to see it, but it's like really different. And so since I have the EPSF done with the 25 brightest stars, I can get the flux of those stars. Then I can use this EPSF to recenter other stars, and then get the flux of those other stars, and so remove all of them. And then in some stars, you can see that here some like white pixels, which are not like residual. It's because some of stars are saturated. So if the center is saturated, I just basically because at this point on the map there is no background, so I just like replace the saturated pixel with like a kind of small white noise, and then I re-add the background to avoid like too smooth region due to saturated pixels. Okay, so just here I just like make a circle around all the stars which are removed, so you can't see them anymore because they are removed, but there is still stars here previously. So just here, just to see before after, you can see that all those big stars which are just like not anymore there, just like all the stars removed, but you can see that there is still a lot of points which are the galaxies. So this is the next step. So just like I make just like a small like zoom to allow you to see all the work which has been done, and you can just see that there is almost anything left, except for like you can see almost like in the really course of the main. In comparison with the intensity of the galaxies, you know that here the stars are much more bright than the galaxies. So this is a big trouble to try to remove the galaxy, and then you can see that the more bright objects are obviously all the time the galaxies. So it's like not any more problem. But this is why I need to really remove properly the galaxies, is to just like remove properly the stars to be able to remove then afterwards properly the galaxies. So here you have I'm using a map. So this map is like 100 arcsecond by 100 arcsecond. I'm using this map to try to recreate a new map with galaxies. So here it's a GIF. So you can see that starting from a white noise. So this is like this is the starting image. So you see the white noise. So you can't see anything but white noise. And this like step by step, the synthesis process is creating stars. So you can see that right now it's not yet working because I told you that it's really it's a very new stuff in this kind of WPH statistic. And so this is what will be my work in the coming months in Paris. It will be to just like find a better way to estimate the galaxies. But you can see that it's not that bad. You can see the structure. You can clearly see that it's like galaxies. It's not look like stars. And so this is the first part. The first part of the removal of the stars it's good. So just like to make a small conclusion on my work. So we want to analyze the coupling between the magnetic field and the dust in a statistical way. And this is the main focus on the statistical way. So we want to get the statistical properties. So we want to remove the stars and the galaxies. And what we have already done is that a good removal of the stars using like the EPSF and WebPSF. And right now, we will try to adapt the WPH to separate galaxies from the dust. Thank you.
I was going to interrupt the talk. Wait, this is the end of the talk? You're good?
Yeah.
Okay, perfect. So I'm going to ask for questions, but can I steal the first question while I pull for other questions? Go for it. So have you done this with like synthetic injection tests where like you know the PSF beforehand and then you like, I guess like this is all real observations, right?
Yeah.
So have you done the same thing with like synthetic observations and like artificial star tests and like confirm that you're recovering the right answer?
Not really. No, we did not like the only false stuff I use is only the web PSF, which is a theoretical one, but did not have tried those things with like we have only tried this with like you can see the CID, but the removal of the galaxy has never been done even with like simulations.
How do you know that you're getting the right answer, I guess, question. Like how do you validate this? Is, I guess my question.
So which part do you mean? Like, oh, I will be sure that I have properly removed the galaxies?
Yeah, I guess, yes.
So I think it will be like exactly like when you see that. Like maybe you can. So yes. Oh, can we know that this is the proper one? Just because, like, I mean, like, you can see it. I mean, like, we're trying to remove structure, so we are just.
Yeah.
It's not precise point. We're just trying to extract two different structures from one map. So if we are able to just like extract those two different structures, and you can see by the difference that there is no like remaining of dust here because like it's like a heavy structure, right?
Yeah.
So if you just make the difference between the two maps, and it seems to be good.
Yeah. Yeah, no, I'm not like trying. This is all great. I'm just curious whether there's a way to additionally test it where you know like the true dust distribution from like a simulation, and then you can inject some like synthetic CIB or synthetic like galaxy population where you know exactly what those galaxy profiles are like you know, and then you know what the truth is because you have like the underlying simulation, and whether that would help you build confidence or not. But it's
I guess it would
all
be
great,
easier to do on the field where you only have galaxies. I don't know what is the most common now in James Webb data. You get more field with only galaxies, more field with only dust.
It depends on where you're looking, right?
Yeah.
There's always galaxies.
Yeah.
Galaxies
There are always
everywhere.
galaxies, but can you get a field where you have almost no foreground and basically only get galaxies? And that's why we are using the other position, the off, because there is almost no dust.
Yeah.
There is some.
Yeah.
So that could be that's why it's our reference. We consider this is the statistics of galaxies.
Yeah.
But yeah, if we had a cleaner field with no dust at all, like a high latitude field, maybe that'd be better.
Yeah.
But then we would need to have something that has the same PSF, so something that is being taken around at the same time, something that is public. So yeah, we use what we have. Yeah.
So I have two questions. One is related to actually detector effects. So for example, like 1/F noise or snowballs, you seem to have one in one of the images that you showed. So how are you accounting for those? Have you developed your own beefy way to remove those, or are you using what's available?
So yes, so in fact I think I have only snowballs in like the other map, the off. Where is this?
You had it in the more recent one. Yeah, not in this one. You had another one with it. I think the next one maybe. You had one with a snowball, or with a removed snowball that showed. I mean, it was. Clear,
Oh no, okay. Maybe it's okay. Why is there is like this kind of halos? You can see like on some like remaining.
Yes.
So okay, so this is because. So where is this? So here you can see like you can see this kind of halo, right?
Yeah.
So yes, it's stronger right there. Okay.
Yes.
So this is okay. So because when I'm doing the EPSF, there is several reasons. So when I'm doing the EPSF, like when you see like where is the EPSF? So in fact there is still some those pixels are non-zeros. So there is still some small values. So when I'm multiplying this pattern by like really high amount, you can have like small defects due to the estimation of the background in those regions. And this is what you can see in here. I don't think you can see that almost like in this kind of region there is like more different structures on those regions. So this is one of the reasons. And the other reason is that my PSF is not really perfectly working on the core. But my main trouble is the arms because I don't want any contamination of the dust because of the arms. So I'm not really caring about the center. So what basically I have to do, what I did, is just like in the center because it's the PSF removal is not perfect. If there is still too much intensity, too much by pixel, I just remove them and replace them by random like white noise plus background. So here you can just see the limit between where I just like remove and change the pixels by like white noise. So here you can see that I remove the arms, so you can't see the arms. Then you have the real measurement, and on the real core, it's like white noise plus background. So this is why you have this kind of effect of halo, which is not due to snowballs.
Oh.
It's just due to the fact that the way I remove it at the core, it's just I'm just like using white noise at some point. And when I'm just like, for the like 10 by 10 center pixel for most of the stars, because this one is like a really, really bright star. This is why you can see it, but on most of the stars, which are those ones, you can't see anything because it's like 5 by 5 pixels. So it's just like almost anything. But on those kind of things, it's like maybe like you can see like maybe 20 by 20 pixels, which are just like removed and replaced by white noise. This is why you can't see those like limits between the core and the arms.
And can I sorry. And my second question is, how well do you need to do this? Like, what do we learn about the ISM dust? That, like, if you, let's say you take a power spectrum or some sort of decomposition of structures at different scales, what do you distinguish between one kind of set of structure and another set of structure? What is the fundamental science question that you're trying to answer?
I mean, like, with those maps, I mean, like, the coupled separation is not like, I'm using this coupled separation only to be able to compare the magnetic field to the dust, to see the anisotropies in angle of the dust. So to do this kind of statistical analysis, I need to just have the largest mass as possible, the largest map as possible. Okay, and when I need to have a large map, I need to remove all of those. So I don't have any like scientific purpose just to remove the stars. My goal is just to study the dust, which is under those.
I had a related question.
Okay.
Like how, when you showed, you just like blurred the map and then had like a residual map that showed a lot of the galaxies.
Yep.
What, like, is just subtracting like an empirical correction for point sources and galaxies like not enough to do that anisotropy analysis?
So yes, maybe it's also due to the fact that when the picture I'm showing you are just like much less precise than the actual map of Jameson. So when you see those one, you can see that okay, those maps are really look like almost the same map, but it's also not the same map. It's really blurred in comparison to those maps.
Right, but I mean using like if you use the blurred map, and then I think maybe on the next slide you show that like if you just like remove that map, does that do a good enough job? Or is it still, are the residuals still too high? So why you have to like more precisely model the galaxy structure?
You can get the top.
Yeah,
So,
I guess I mean it's a similar question to Andrea that like why I'm also interested in this. Seems like a really cool science case, and so I'm trying to understand like why the precision removal of the galaxies, which are on different sort of spatial and angular scales as the dust structure that you're seeing in this super high resolution map, why that is so of such importance. Does that make sense?
Yeah.
I think maybe what you can, yeah. Okay, so the WPH expertise in Paris is not me, but basically why do we know what coefficient in the WPH set traces the dust and traces the galaxy, which is a question that I've asked.
No.
So that's one of the issues, that you cannot just say that WPH coefficient is for this structure. There are some coefficients that we know what they are, but then after that it's too complicated to figure out which is which. So you really need to remove the object from the data to then get the statistics.
Yeah.
And like sat close to the image, a lot of the kind of feathery striations in that image are on one axis at least as compact as the galaxies, and as well. So I can imagine how if you took a power spectrum of that, it would galaxies would mess you up.
Yeah, there is like many small variations are just like removed by the blow estimation, and this is like what we are looking for when you are studying this map. From just we need like a really high resolution to be able to see small like statistical differences in small scales, and this is why we need like a really clean map, and we can't just like make the map blur to be able to just like remove the galaxies.
So in addition to the pause at 335, the 335 filter, you're also going to get some contribution from scattered light that's coming from the star cluster. So it's not just going to be the pause and that band. It's going to be mostly pause, but you may actually get some contribution from scattered light from the dust, which is a little separate from the pause. Is there any plan that you guys have to remove those, or do you not really need to remove that for your science case?
I think we don't really need to remove them. I think like,
Sorry.
not that much. Like we the only like thing we need that we need to remove, which is not on the plan, is obviously like the myopia arms. It's the big like problem, but I mean like except for this thing, I think we don't need to remove any other stuff.
Mm-hmm.
So I don't know if you mentioned it in one of the first slides. So we have 335, we have 277, we have 200 and 212.
That was going to be my next question.
So there's a plan. There's a plan to actually try to decompose not the physical components, but the emission components, also, right? So at 212, we need to remove the background and stuff like this to only have H2. Maybe at the dust level, at 335, we should also try to remove the stellar component and stuff like this. Yeah.
Mm-hmm. Do you have anything higher than 335?
No.
Okay. 360 could help, but 360 also has a ton of pause in it anyways, so it ends up adding a layer of complication.
I'm going to preface this by saying that I'm terrible at mathematics, and I do not understand how CASA cleaning works, and that it's a black box to me. This feels very similar to like radio interferometry cleaning of dirty images. Is there some parallel here where you could use the techniques there in order to like pull
Don't
out?
look at me. Don't look at me. I said I'm not the expert. 2 months ago he came and he explained to us, and I was like, oh, that's cool.
Okay.
So I don't know.
Like, are you familiar with radio interferometry and like the sort of processes that go into cleaning dirty images there?
Not really. No.
Yeah, I mean, it basically involves, right, every baseline that you have is a sinusoidal function on the sky that gives you an intensity. And then from all the different baselines, you have, like, you cover different angles and different size scales. And it seems, I feel like the wavelength analysis you were showing felt similar to what goes on there. But I'm just wondering if there's some parallels there where maybe the technique kind of exists in the radio astronomy community, but I don't know at all.
It's kind of like doing the opposite, right? Like the clean algorithm makes everything a point source, tries to get all your point sources, and then this is trying to remove all point sources.
Not point sources,
Well,
right,
Certain
like
structures.
but there are some major differences in the way an interferometer works, because you have introduction when you go from the UV domain to the image domain, you spread your information over the entire image. So at any point you have a convolution of everything. Whether that may not be necessarily the case for this kind of study. So your assumptions are different. So.
Okay, I said I'm bad at math. So.
No, I mean.
I'll bring it up to the experts. Maybe there's a connection somewhere in their expertise, because they're also doing radio.
Yeah.
So.
Okay.
Chris, and then.
Oh no, I'm just.
Oh, okay.
I'm just moving around. Sorry.
I was wondering, what is there a paper reference for that Herschel CIB subtraction? I didn't write it down, and I really want to read that.
I think it's only submitted. I think it's not already archived.
It's not the archives.
Okay,
But
I'll clarify.
it should be like in a few months. It's already.
It's on the archive.
It's really new. Even those techniques with like not dense structure are really new. This use of WPH is really, really new. So sometimes it's a kind of black box, and we don't understand, in fact, all the coefficients we are using. But at least it seems to be working.
As long as it's like, you can do a source injection version of that. You can take one of the empty Herschel cosmological fields, stick M31 on it with another map, run it through this, and test what you get out. So it's testable. A testable black box is fine.
Isn't it one thing? He sent an image, right, with the new synthesis or the new decomposition. He sent us an image just with one galaxy in nothing, and he was able to reproduce it. Constant, wasn't he? Like a few weeks ago.
It was not a galaxy.
Oh, it was like a big blob.
A galaxy.
Yeah, exactly.
Oh, yeah. You mean, but it was using the new WPH,
the new code, yeah.
which are even more
Black box. Yeah, it's like
it's just a brand new stuff. So we don't exactly know if it will be working, but they are trying to make new WPH program to be able to just like work on more dense structure, because those ones are first been made to like remove these kind of structure which are not that dense, and so they are trying to make new kind of WPH stuff to be able to remove more dense structures. But it's like really new from like 2 or 3 weeks.
Can I ask another question? Can you go forward where you show where your perfectly cleaned image?
Sorry, at the end you mean?
Yeah. Yeah. At the end. Yeah. Right. This one. So this is you're saying. So this is a single band, right?
Yep.
And you said you had multiple bands. So I'm curious whether there's any would fitting multiple bands at once or incorporating information from multiple bands improve this fit in any way? Since it's like there's extra information. So I'm curious whether like there's any plans to do like a multi-band analysis or whether that's useful or like what the other wavelengths could add in terms of informing the contamination.
Yes, as I mentioned, the goal of the work proposal is using. So we have also H2 maps because we want to study the global goal is to study the ambipolar diffusion, and then you need to have PAH and H2.
Okay.
And since in my work is only focusing on this one because I think that the H2 map is like worse because of like strange call interference when they're just trying to make the mosaic. So this is the best map because like somehow you can see sometimes the effects due to the superposition of the different calls. So this is I think the cleanest one, and the other one are just like worse. In those cases, it could be like a problem when you want to remove structures, and if you have like other structures due to the calls.
But if we had a map at a different wavelength that did not show as much diffuse emission, we could use that to, assuming that the galaxies don't change too much between one and the other in terms of statistical, 2D statistical representation, we could. For the stars, no.
Yeah.
Because the PSA is going to change, I think, enough from one wavelength to another. But for the galaxies, maybe.
I mean, if you're for the galaxies that are reasonably low redshift, where the 3.3 par feature is also in the band for those, if you go to wavelength and the par feature also drops out of the band in the other band, then your foreground galaxies would both be a bunch beta. So, but would be for some, would be for others. That could get a little messy.
Yeah, could be something to look into.
Any other questions?
I had one, but maybe it's not. So the group that started this, they are the one also who did the Planck decomposition. You know, who went from decomposing the foreground and something. I don't know if François mentioned that to you, but were they using like WPH like 0.1 type of version of code to do this sort of decomposition? Do you know anything about that or not? No? Okay, that's fine. I don't know if that was the same technique that they just improved or it was something else. When they did decompose all the Planck, foreground, background, everything.
Okay, let's give another round of applause.